Today is 3rd of August 2025. I want to talk about how we should see the transformer and yeah, let's do it. Let's do it.
Slightly closer to the targets. And now all we have to do is we have to do a pass. So
Note.
we've done the forward pass and it's still lost. Now we can tap backward.
I can't see any note here.
And we can
wait a second. Just wait a second.
And now we should have a slightly lower loss.
Document. Okay. Transformer.
And okay, so
Box is coming.
The backward pass.
So
loss is 3.66.
Last time I talked about
3.47.
Self-attention. Self-attention in very key value viewpoint. I want to this time more extended. It was self-attention. And this time I want to talk about the more structured story, which is first, positional encoding. Why are we doing encoding? Because LNN receive inputs sequentially by a position, but transformer don't, so they need positional encoding. So by positional encoding, they got new vector, which is from this and this. I think one of this is positional encoding. How does it encode side? You can use take token that get encoding, or you can use others. So embedding layer can be made. And so if you embed it, then X, let's do transformer is sentence, then let's it can be 1, 0. Do is let's do is 0, 1. Transformer equals to 1, 1. In this case, then the dimension, what dimension? The dimension is 2, and I forgot what dimension was it. There was some keyword. Which dimension should it be? Okay, anyway, so then based on this, we can calculate query. Wait a minute. Then there will be score matrix, which is 3 by 3 will be come out. I think I'm missing detail here. What query is come out here? And there will be softmax come out. Softmax is done by attention weight multiply by value matrix. And there will be also paddings. And there will be, this is kind of flow of encoder. And if we make it as code side, then there will be sublayer. And there will be multi-head attention. And there will be feed, forward, network, and encoder modules, and so on. And for decoder, we need masking here. We validate the loss. But for each neural is data. And we first do forward pass, then we do the back pass. That's gradient descent. And then we should be able to iterate this, and we should be able to print the current step, the current loss. Let's just print the sort of number, the loss. Yeah, I think I'm missing details here. That should be it. And then the blocking rate. So 0.1 we saw is like, yeah, if we go back to this self-attention, I think I need more improvement in this explanation. If we go to this key query value, there is no runnable parameter, and there is no tensorized beds, and there is no projection matrix.
You see how we've actually converged slower in a more controlled manner and got to a loss that is very low. So I expect widebread to be quite good.
And there's no positional embedding, no multi-head, and so on, no masking, no padding. So we need to develop why.
We actually have a terrible bug in here.
And we should also talk about the dimensional size. When there's token exists from X1 to XD, and there will be positional vector and yeah, H0 vector H0 E will be E has the plus positional vector, and there will be pre-layer norm, and there will be attention, and the query very query value and key metrics will be weight metrics will be updated by backpropagation.
And then we do backward and we fill in the gradients. And then we do it, but we don't flush the graph. It stays there. So when we do the second forward pass and we do backward again, remember that all the backward operations do a plus equals on the graph. And so these gradients just add.
Yeah, so if I add some details,
so basically we didn't zero graph.
There will be key query value matrix.
We need to enter all the parameters. And we need to make sure that p.grad is set to 0.
And for each of the word, yeah, I think this is the key thing. For each of the word, we will calculate Q query value.
We reset each grad to 0, so that we do backward. All the 0 and the actual backward pass accumulates the loss derivatives into.
And then we can calculate similarity after calculating Q query value. After calculating Q query value, we can calculate similarity, which is using attention score. Attention score is calculated by Q and queries inner product, and we will normalize it. After normalize it, we will calculate attention matrix multiplied by value matrix. Then we can ask how QKV is different than why we do some special jobs. We do special jobs, and the differences is between and fixed in linear algebra viewpoint.
Really good. We can try to step a bit greater.
And yeah, for transformer metrics, the important thing is it only has decoder. I mean, GPT only has decoder. And for decoding, it use self-supervised method, which is move right shift. So from the first length place, it predicts next token. It's what it does. And for BTC,
mathematical expressions in case of modality percent problem that take input as the data and they take input the weights and the parameters of the neural net. Mathematical expression for the forward pass.
Thank you. I will improve tomorrow.
To measure the accuracy of the predictions. And usually